So hello everyone. Today we will be doing problem sessions where we will be discussing all the problems related to whatever we have discussed earlier. So here is the first problem. This first problem states that consider a system of four half spin particles with magnetic moment mu naught, and they all are located in an external magnetic field. So basically you have four spins which can be either up or down, right? So these are the spin 1, spin 2, spin 3, spin 4. 1, 2, 3, 4. So these are placed in an external magnetic field B, or let's say H. Then find out what are all the quantum states and what is all their possible energies. So how to do this? Again, if you see, this problem is very simple. As we have done the three spin systems and three half spin particles. So there you also have for one spin you have two choices, up or down. So here for four spin particles you will be having how many such possible combinations? That will be 2 raised to power 4, that will be equal to 16. So you will be having 16 different arrangements here. So let's try to write them. So how can you write them? So first of all, you can consider that the spin 1, it can take all the 8 values up to here, all up, and 8 values down. Then 4 values for spin 2, 4 values up, down, right? I hope you can write this. And then similarly 2 up, 2 down, and 1 up, 1 down. So you can write all these 16 possible combinations, right? So these are all the possible quantum states, and what will be their possible energy? So now the energy is given by minus mu dot b, where mu is the magnetic moment. Now for the first combination, that is all the magnetic moments, they are all in the up direction, right? So the net magnetic moment will be 4 times mu naught. So the total energy will be minus 4 mu naught b, right? And similarly you can write energy for all of the 16 cases. So now here let's try to understand one interesting thing that is coming from the binomial distribution. So now if you note here 4CR, where 4 is the number of particles, right? And this R is representing how many up particles are there, or let's say down number of up spin. Okay, so now if you remember this 4CR formula, then you can find how many particular combinations are there with particular energy. So if you see here, in out of these 16 combinations, you will see that some of these energies are repeating, just like this minus 4 mu naught b, it is coming one time. Similarly this 4 mu naught b, it is coming only one time. But this minus 2 mu naught b, 2 mu naught b, 2 mu naught b, 2 mu naught b, so basically they are coming on 4 times. So if you see here, this 4CR is representing the number of ways of arranging the 4 particles, out of which R or R, basically are of same type. Here let's try to see this by example. When energy is equal to minus 4 mu naught b, then what is the case? So here all the particles all are in up state. So here in how many possible ways you can arrange all these up particles? So you can arrange 4 particles, out of them 4 are in up state. So there will be only one possible way. Now when you have energy is equal to minus 2 mu naught b, right? Then in that case you will have such a situation like you have 3 ups and 1 will be down. Then only this will cancel, and this 2 will give you 2 mu naught magnetic moment, right? Now this you have to arrange four particles, out of which three are of same kind, right? So you can arrange them by 4c3, right? So what will be the 4c3? That will be 4 factorial divided by 3 factorial and 1 factorial, right? So that will be equal to 4 ways. So you can arrange these particular combinations, this particular arrangement in 4 different ways. And then similarly you can do it for when the energy is how much? This is 0. So third case, when energy is equal to 0. So energy, how can energy be 0? When you have 1 up, 1 down, 1 up, 1 down, right? Then only this will be going to give you a net magnetic moment 0, right? So how can you arrange four particles? You have to arrange 4 particles, out of which 2 are of same kind, right? And then the remaining two out of the remaining two are of same kind. So that will be equal to 4 factorial, 2 and 2 factorial, right? So if you do this, that will be 4 times 3 divided by 2. So this will give you 6. So you have 6 different ways and you can arrange these 4 spins to give this final energy as 0, and then you can do this for the remaining thing also. Now if you notice here, you have a pattern. This pattern is like 1 4 6 4 1. This 1 is representing the number of possible ways in which you can arrange the system to give you a net energy of minus 4 mu naught B. Or this final 1, it is representing the number of ways in which you can arrange the system to give 4 mu naught B energy. Similarly, this 4 and this 4 and this 6. So this is what a binomial distribution is, if you remember in the previous lectures also. So using this example, I hope you will get the feel of like how we should use the binomial expansion, or this is basically a binomial expansion series, right? If you see here, so with the coefficients are NCR. N is the total number of particles and R is the number of one type of particles. So I hope you can do this problem by yourself. Let's try to understand the next thing. There is a second part to this question which says that suppose the system is isolated and known to have a total energy of minus 2 mu naught B, and then we have to list all the state. So what we are doing here, we are putting a constraint. So if there is a constraint in the system that the total energy is fixed, right, then what should be the what will be the different arrangement of energies? So here, if you see here, if the total energy is minus 2 mu naught B, then you have 4 such combinations, right? So let's try to write all these 4 combinations there. So these are the all 4 combinations which can give you energy total minus mu naught B, right? And then therefore you can conclude that with the energy constraint, the accessible states has been reduced. So that is one of the important point you should note, that whenever we put constraint in the system, that the accessible state will be reduced. Now here also, let's say that this what will be the here, what will be the equilibrium or the average energy? So that will be minus mu naught B. Now from the ergodic hypothesis also, so to achieve this minus 2 mu naught B, the system will go through each of these 4 states, right? That is what we have discussed earlier in the ergodic hypothesis also, that the phase space point will move through all these 4 states before achieving this equilibrium, right? How the equilibrium is achieved, that is what we have discussed here also, and you can understand that by this problem also. Okay, so let's try to discuss another problem. This is a problem of composite system. What a composite system is, so basically you have a system of two or more subsystems. So here what you have a system A star, which consists of two subsystems A and A dash. Okay, and these two subsystems, they can interact to a small extent, right? And thus they can exchange energy with each other. Now the system 1, uh, it consists of three spin half magnetic moments, right? And the magnetic moment they have is mu naught. And let's suppose the subsystem 2, which is A prime. A prime consists of two spin half particles, but the magnetic moment here, each particle have a magnetic moment of 2 mu naught. Okay, I hope you understood the problem. So basically you have a system A prime. Here you have A and A dash, right? This is also spin half particle, this is also spin half particles. Here you have how many? 3 spin half particles, but the magnetic moment is mu naught. Here you have 2 spin half particles, but the magnetic moment of each particle is 2 mu naught. Okay, now this system is placed in an external magnetic field B, right? And then we have to write all the possible state for this system. And we will do this second part later. So what will be the combinations? So we will be writing this problem in two parts. Okay, so for the system 1, which this has magnetic moment as mu naught, right? So, and you have 3 spins, spin 1, spin 2, spin 3. Then you can arrange all these spin 3 in how many different ways? 2 raised to power 3, right? Because you have 2 choices and you have 3 particles. So that will be 8 different ways. So you can list all these 8 different ways. And you can also calculate the corresponding energy. That will be minus mu naught B, or mu B, let's say. Mu will be the magnetic moment. Right? So you can list all these 8 possible state for system A. Now for system B, where you have, so here you have 3 particles. Now here you have 2 particles, but the magnetic moment is 2 mu naught B, 2 mu naught actually. So you can arrange these states in how many different ways? 2 raised to power 2. So that will be 4. Now, therefore, for the system, the total system A prime, how many different number of microstates we have? So we have 2 raised to power 3 for the system A and 2 raised to power 2 for the system A prime. And now, since these two systems are mutually exclusive, then the total number of microstates will be just the multiplication of the two things. So that will be 8 times 4, that will be 32 states. So for the system A prime, you will be having 32 states. And actually, this is not possible for me to write all these 32 states, but I can tell you how you can understand all these 32 states. So what you should do, you should take this first column, first row from this system A, and you take all the combination from these columns, right? Then you will get total. What you will get? You will get U from the system A, and then you can get, let's say, UU from the system A prime, or you can get UD from here, or you can get DU, or you can get DD. Right? For all these 4 states, you will here you have UUU, here also UUU, and here also UUU. So in this way, you can, for this first serial number, you can get all the 4 states, and for all these 8 states, you can do the similar exercise to get a total number of 32 states. Okay, I hope you got this problem A. And now let's try to see how many possible different ways we can arrange the system so that the total energy of the system will be minus 3 mu naught B. Okay, so if you see here, here in the system A, the maximum energy what we can get is basically the plus minus 3 mu naught B, right? And in the system A prime, the two endpoints are plus minus mu naught B. So, and in between they have these two values, right? Minus mu naught B and plus mu naught B here, and here 0 is the energy. Now we have to make the combinations of these two systems to get a total energy of minus 3 mu naught B. So in how many ways we can get this total energy as minus 3 mu naught B? So what we will do, we will make a combinations, right? So the first combination will be such that the system A, if this is system A and this is system A prime, then if the system A prime have minus 3 mu naught B energy and the system B, it has 0 energy, then in that case we can get minus 3 mu naught B energy, right? Or what we can have, what will be the other case? So that can be, here we can have minus 1 and sorry, plus 1 here, and then minus 4 here, right? In that case also we will get a total of minus 3 mu naught B. Now there is, I think, no other possible combination in which we can get this total energy as minus 3 mu naught B. So what we will be doing? Is we will make such combinations from this and this. So for A minus 3, you will get only this particular state, and then you have to combine this particular state, basically one serial number with A prime 0 0. So basically you will combine these two, B and C, right? So one will combine with B and C. This is the first, and in that case, how many combinations are there? There are 2 combinations. Now this minus 4 here, this A situation here, it will combine it plus minus 1 here in the system A. So plus minus, sorry, plus 1. So plus 1 will be here, here, and here. So basically you have 3 cases, 4, 6, and 7. So you will combine 4, 6, 7, and 8 with A. So you will get three such combinations, and you can list all that. You can take all these combinations from here, and you can list it here for system A prime. So this is the total number of possible ways in which you can arrange the system so that the total energy of the system, basically A star, it will be minus 3 mu naught B. Okay, so this is how you can solve this problem. Okay, so now there is an interesting problem from PFI. So this particular problem states that consider a system with 3 energy levels under equilibrium. So you have equilibrium and you have 3 different energy levels. So let's say the energy levels are such that this ground state is 0, and then kBT, and then 2 kBT is the energy stage. And it is given that the total energy of the system is given as 42.5 kBT. Okay, so now we have to find the total number of particles in each of these states. So how many particles will be there in N1, N2, and N3 state? And find the probability for the particles to be in each state, and then find the average energy of this system. Okay. Now let's try to approach this thing. So we will be solving this number of particles in each state from Maxwell-Boltzmann distribution. So what is a Maxwell-Boltzmann distribution is? So it states that the ratio of particles in two states is given by e raised to power minus beta e, where this e is the this gap of the energy level, gap between the energy levels. This n is the what does this mean? So this means that N1 will be equal to, let's say N0 here. So n1 is the number of particles in this zero energy state, and n2 will be, therefore n2 will be, from this, that will be n2 e raised to power minus beta e. And from here, if you see, this e is nothing but kBt, or I can write kBt as 1 by beta, right? So this n1, n2 will be nothing but n naught e raised to power minus 1. Okay, now what is this? N3, right? So N3 will be N naught e raised to power minus beta 2e. Since the gap is between these two levels is 2e, so that will be N naught e raised to power minus 2. Okay, I hope you can follow me up to this point. Now, the total energy. The total energy will be this number of particles in first state, then number of particles in the second state into that energy, and number of particles in the third state multiplied with that energy. So the total energy of the system is nothing but the multiplication of the number of particles with the energy of that particular state. Okay, so for in the first state there are n naught particles, but the energy of that level is 0, right? And in the second state, the number of particles are n naught e raised to power minus 1, and the energy of that state is kBt. And in the third state, the number of particles are n naught e raised to power minus 2, and then the energy of state is 2 kBt. Okay, so what will be the total energy? So the total energy in that case is n naught kBt. You can take common out from here, and then this will be e raised to power minus 1 plus 2 e raised to power minus 2. So that will be the total energy. Now it is given that its value is around 42.5 kBt. So that you can find the value of n naught as 42.5 and divided by e raised to power minus 1 plus 2 e raised to power minus 2. And now if you solve this using calculator, then this value will be coming around. How much is this value? It is 66.55. So this is the value of n naught. N naught is the number of particles that will be in this zero energy state. So from here, using these equations, you can find the value of n2 as 66.55 e raised to power minus 1, and this value will be, how much is this value? This value is 24, around 24, let's say, and the value of n3 will be around 9. Okay, so this is the number of particles that are in all these states. So, and the total number of particles will be n1 plus n2 plus n3. And if you add all these three numbers, you will get around 100. Okay. So these are the first question is done, the number of particles. Now let's try to find the probability for each particles to be in each of these states, right? And then we will be doing we will be finding the average energy. So the probability for each particles to be in all these energy levels. So for in the first state, the number of particles are around 66, right? And the total number of particles are 100. So the probability will be around 66 upon 100. And in the second energy state, there are around 24 particles out of 100. So the probability will be 24 by 100. And in the last, it will be around 9 out of 100. So this is the probability for the particle to be all these states. Let's try to plot these probabilities as a function of energy. So here you have 0 energy, then kBT, and then 2 kBT, right? So let's uh, write this 66, the numerator factor only. So 66 will be here somewhere, let's say. 24 will be here, and then 9 will be just below this. So if you plot this, then you will get a exponentially decaying type function. So this is nothing but this beta e. So this is the probability of for these particles to be an energy of to be lie in the energy state ei. So this is a exponentially decaying function of energy. So you can also understand this from this fact that as you go higher in the energy levels, the number of particles will be here in the top state will be very much less than compared to the lower energy levels. Now let's try to find the average energy. So you can multiply the probability with the this probability of each of these states with the energy. So in the first energy, the energy is 0, and the probability is around 66 or 67, let's say. In the second, the probability is around 24, and energy is kBT, and then 9 and 2 times kBT. So if you solve this, you will get 0.42 kBT, which is nothing but the total energy divided by number of particles. That is 100 particles were there, right? And the total energy was 42.5. So if you divide this, you will get the average energy also. So in this case, this is how you can approach this problem. Now here comes an interesting problem. So this problem will also be related with the binomial distribution thing. So here what we have, you have a system with volume V, inside which another system V naught is there. Okay. Let's suppose n be the capital N be the total number of particles. Then we have to find the probability P of such that out of this capital N particles, small n number of particles are there in small volume V naught. So this is the situation. So here you have a total volume V, and inside this you have V naught V naught as the small volume. Now, if capital N is the total number of particles inside this region, then we have to find the probability that out of this capital N, small n number of particles will lie inside this small volume V naught. So basically, this problem is also related to yes or no. Basically, whether the particle is inside V naught, yes or no. So basically, so we will be using binomial distribution to study this. So how we are going to study this? So we will be assuming that let's suppose n is the number of particles. Number of particles in V naught, right? Then what will be the remaining number of particles? That will be n minus n number of particles. Then n minus n number of particles will be in V, right? So that is what the situation is. Now, the probability that whether this particle, the particle is in V naught, how much will be the probability that the particle, whatever we are considering, a single particle, one particle is V naught. So that probability will be nothing but the ratio of the two volumes, right? So this V naught divided by V, right? So this is the probability that the one particle is in V naught. So therefore, for n number of particles to be out of capital N to be in this particular volume, so that will be in how many different ways we can arrange n particles small n particles out of capital N inside this particular V naught. So this will be the NCR, right? NCR formula. What will be the probability of each of these particles? That will be V naught by V. So this particular formula is representing the probability that n number of particles will out of capital N are in this volume V naught. So this is how you should approach this problem. Okay, so now let's try to do a problem based on this particular solution of this problem. So the problem will be solved using Monte Carlo simulation. I will tell you in a minute. So let's try to define the problem. The problem is here. So you have a complicated shape here, okay? And you want to know what is the area under this curve, right? So by any other method, it is very difficult to know the area under this curve, right? So, but what you can do, you can also always like inscribe this particular unknown area inside a known area. So let's suppose this A is the known area and A prime is the unknown area. Okay, it could be volume also. Then that will be a different situation. So let's try to play a dart game. So, but what we will do, you will place this area here, and then you will throw darts on this particular area. So this capital area A, right? So we will throw all these darts here. So some of darts will fall inside this A prime also, right? So let's suppose you have throw total capital N number of darts in this total area, right? So out of this total capital N area, capital N darts, let's suppose small n darts will hit A prime, okay? So now this is a problem similar to what we have discussed in the previous problem, right? So you need to know whether the dart is hitting inside this A prime or not, right? So the probability that a dart will fall inside A prime, it will be small n divided by capital N. So what you will do, after throwing n number of darts, you will count the number of darts which fall inside this small area, that is unknown area, right? So the probability will be small n divided by capital. That is an obvious statement, right? Now this particular probability is also equal to the ratio of these two areas, okay? So this particular ratio is also equal to A prime divided by A. So here, from here, this you can find the unknown area in terms of known area. So this is the beautiful application of binomial distribution, right? So here you can use a known area to find, and just by probability calculation, you can find the unknown area. Now, in modern simulations, basically what you can do, you can generate these random numbers, right? And then you can calculate this unknown area using computers, right? Computer simulation. So that is what a Monte Carlo simulation is. And it is all basically based on probability calculations, okay? So that is it for today. We will be meeting in next class. Thank you for today.